Let's compare the Greek alphabetic and acrophonic numeral systems with positional notation. The aim is to provide context and clarity for modern mathematical notation. Let's begin with the Greek alphabetic numeral system. Over here we can see 27 letters arranged in 3 rows. The first row contains the letters alpha, beta, gamma, delta, epsilon, digamma, zeta, eta, theta. These 9 letters in the first row correspond to the digits 1 through to 9. So we can describe this as a decimal system. It is a base 10 system. But we also have an additional 2 rows. This second row corresponds to the multiples of 10, and this third row corresponds to the multiples of 100. The second row contains the letters iota, kappa, lambda, nu, psi, omicron, pi, kappa. And the third row contains the letters rho, sigma, tau, upsilon, phi, chi, psi, omega, psi. Note that among these 27 letters, there are 3 archaic letters. So these are 3 archaic letters in addition to the 24 letters of the modern Greek alphabet. This letter over here, digamma, represents the value 6. Digamma is an archaic letter. This letter over here, kappa, it is also an archaic letter. Kappa represents the value 90. So that is 9 times 10. Psi is also an archaic letter. So Psi represents the value 900. We have 9 times this factor of 100. So the values for digamma, kappa, and Psi are 6, 90, and 900. So these are archaic letters that are included so that we have this alphabetical order and we preserve these ancient values that have been assigned to these Greek letters. So this is going to give us the starting information that we need to use the Greek alphabetic numeral system. And we're going to compare this Greek alphabetic numeral system to the modern positional or place value numeral system. So for modern mathematics, we tend to use positional numeral systems. And we can choose to work with base 2, which is binary. We could choose base 16, which is hexadecimal. Or we could also choose decimal, which is base 10. And here we can see the prime factorizations of these bases. So binary and hexadecimal are commonly used in computing. And the decimal system, that is a very common system that's used internationally. And you can see that this ancient Greek alphabetic numeral system can also be described as decimal, but it is not positional. It is not positional because we're not reusing these 9 characters over here. Instead, we have additional characters for the multiples of 10 and for the multiples of 100. And for higher powers of 10, we have some alternative notation. So the notation is a little more complicated in this ancient system. These more modern systems, they are a lot easier to use. These are much more convenient when doing computation. So in blue, we can see the hexadecimal values from 0 to 15. And next to that, we can see the binary representation of those values. And notice that for the hexadecimal values, the digits from 0 up to 9 are the same as the decimal values. But then we need new characters. We have to add additional characters so we can get up to 15. And 15 is 1 less than the base when we're dealing with hexadecimal. And by convention, we use the first 6 letters of the Latin alphabet. So that's A, B, C, D, E, F. And these Latin letters are analogous to the first 6 letters of the Greek alphabet. Alpha, beta, gamma, delta, epsilon, digamma. Digamma also has another form which resembles F. So F and digamma are analogous. Digamma is the Greek version of the Latin F. So you can see that each of these values represent a value in hexadecimal that is 1, 2, 3, 4, 5, 6 more than 9. So we have the existing digits up to 9 from our decimal system, and then we need an additional 6 symbols, and that can get us to 15. So over here, with these binary representations, we're dealing with a positional or place value system. So when we have these 4 ones in this example for 15, what do these ones actually mean? These ones don't mean the same thing because the position tells us extra information. So this 1 over here on the right, that 1 is getting multiplied by 2 to the power of 0. So it's the base to the power of 0. And then over here we have the base to the power of 1, then the base to the power of 2, and then the base to the power of 3. So this is actually 8, this is 4, this is 2, and this is 1. And if we take the sum of 8, 4, 2, and 1, that will give us 15. So that is the binary representation of 15. And in hexadecimal, we would just write that as F. So these are modern positional systems. Now we're going to compare the alphabetic and the positional system using examples. So the first example which we will see is the value 2 to the power of 2 to the power of 3. So here we're dealing with a nested exponential, and nested exponentials are interpreted from top to bottom. So first we need to evaluate 2 to the power of 3, that is equal to 8. And if we were using a base 8 system, that would be called octal. And for octal, we would just need 0 through to 7. So we would only need this left-hand side over here. So octal is dealing with base 8, that is 2 to the power of 3. But in this value, what we want to do is raise 2 to the power of 8. And that is 256. And we're also going to subtract 1 from this value to make it an interesting example. So over here we have 256, and we're going to subtract 1, and that's going to give us 255. Let's write that in hexadecimal. So in hexadecimal, that is going to be F, F. And I'll write a subscript X over here to indicate that we're dealing with hexadecimal. So what do these two F's mean? The F on the right is referring to 15. And this other F over here, that is referring to 15 times the base. And the base is 16. So we have the sum of 15 times 16 and 15. And that's going to give us 255. So this is equal to 255 using decimal notation. So this is 250, which is 5 times 10, and then 5. So that's the ones place, the tens place, and the hundreds place. So it's just like what we have over here. Now let's write this using the Greek alphabetic numeral system. How are we going to write 200? Well, we're going to use sigma. Sigma is 200. So first we have sigma. And how are we going to write 50? 50 is 5 times 10. That corresponds to nu. So nu is used to write 50. And what about 5? 5 is represented by epsilon. That is epsilon over here. And epsilon is analogous to E in the Latin alphabet. And you can see that it is 9 plus 5 over here. So that is analogous to this E over here. It's the 5th letter in the sequence. So sigma, nu, epsilon. That is used to represent 255. And we can swap the order of these letters. That's because this is not a positional system. For a non-positional system that uses different letters for these different powers of 10, we are free to move these symbols around, and you can still represent the same number. But for a positional system, the position gives us valuable information. And if you swap the order, that is a different number. You could also write this using capital letters. So you can write capital sigma, capital nu, and capital epsilon over here as well. Now let's have a look at the Greek acrophonic system. The acrophonic system uses a slightly different way of representing numbers. So for 200, we're going to represent that as the symbol for 100 written twice. And the symbol for 100 is actually eta. It's the capital eta. So we can write this as eta, eta. Now, why is eta the symbol for 100? Well, it comes from the Greek word hecaton. And hecaton is where we get the metric prefix hecto from. So you can think of this as hecto, just like the metric prefix. And that's why we're using eta as the letter to represent 100. So we have 200s. This is additive notation. If we write these symbols next to each other, we are interpreting that as adding them together. Then what about 50? Well, we can write 50 as 5 times 10. So 5 is represented by this oddly shaped pi, and 10 is represented by delta. And we can represent multiplication by writing the delta inside of this pi. So why is pi used to represent 5? Well, that's because of the Greek word pente. Pente means 5. And delta means the first letter of deca. So deca, if we spell that in Greek, you take the first letter, that is delta. So delta is the first letter of deca, and we use that to represent 10. And these are actually metric prefixes in English as well. So deca is the prefix for multiplying by 10, and hecto is the prefix for multiplying by 100. So this gives us 250. And what about 5? Well, 5, as we said before, is just pi. So this pi kind of resembles a gamma, but it's a different letter. It is a pi. So this is 5 by itself, and this is 5 multiplied by 10. So this is called an acrophonic numeral system. Acrophonic means that we're taking the first letter of the word for a number, and we're using that letter to represent the numerical value. So that's why pente, the pi in pente, gets turned into the 5. So this is actually the numeral for 5. And that's why if you take the word deca, the first letter in that word is delta. And that's why we're using delta to represent 10. Now, this is very similar to Roman numerals. The Roman numeral representation would be C, C. So C is 100, so we have 200. And 50 is represented by L in Roman numerals. And then V is used to represent 5. So we have 2 hundreds, a 50, and a 5. So you can see that this is, again, additive notation. We write these symbols next to each other, and then we interpret that as addition. Let's have a look at the next example. The next example is 2 to the power of 2 to the power of 4. And this time we won't subtract 1. So first, let's write this in hexadecimal. In hexadecimal, this would be 1, 0, 0, 0, 0. And I'll write a subscript x because this is a hexadecimal number. So we're using positional notation over here. And if you wanted to write this out in binary, each of these zeros would actually be 4 zeros. So over here, you would have 4 zeros, and in total, you would have 4 times 4 zeros, which is 16 zeros. So 1 followed by 16 zeros. That would be the binary representation of this number. And again, we're dealing with nested exponentiation, so we interpret from top to bottom. So first we evaluate 2 to the power of 4, that is 16. So this is 2 to the power of 16. Now, what is that using decimal notation? We can write that as 65,536. And now we're going to have to use a slightly different type of notation to extend this alphabetic system. So we don't have unique symbols for thousands or for tens of thousands, so we're going to have to reuse these symbols over here. So let's see how this is going to work using the alphabetic Greek numeral system. So first, we're going to consider this 60,000 as 6 myriads. A myriad is 10,000. So we have 6 myriads. We'll write this as a capital mu. This is mu for myriad. And then above that, we're going to write d gamma. And d gamma means 6. So we have 6 myriads. Then we have 5,000s. So we're going to use 5, which is epsilon, and we're going to put a little mark over here. And this mark is telling us to interpret this as multiplied by 1,000. So we have epsilon, which is 5, and we multiply by 1,000. That gives us 5,000. Next, we need 500, and we have a letter that represents 500. That is phi. And then we need 30. We have a letter that represents 30. That is lambda. So lambda represents 30. And then for 6, we have d gamma. That is d gamma. So here we have the mu, which represents a myriad. So this gives us 6 myriads, then 5 thousands, and we have 500 and 30 and then 6. And we could also swap the order around and it would still make sense. So it would still be the same number. But it's much clearer to have a set convention where you start from the largest values and then you go down to the smallest values. So this is one way of writing it using the alphabetic system. Now let's have a look at the acrophonic system. So again, we're going to need 6 myriads, and we're going to use mu to represent a myriad. But 6 is the same as 5 plus 1. So we can use this notation for 5, which is this oddly shaped pi. And inside of this, we're going to put m, or mu. So m and mu are counterparts, and the capital letters are exactly the same. It's just the lowercase letters that look different in the Latin and Greek alphabet. So here we're going to put a mu for a myriad, and this is getting multiplied by 5. So this gives us 5 myriads. And now we need an extra myriad. So I'll write another mu, and this gives us 6 myriads. And then we need 5,000. So we're going to again have 5, and then we're going to multiply by 1,000. And 1,000 is represented by chi. Now, why is this chi used to represent 1,000? Well, it's the same root as the metric prefix kilo, like kilogram or kilometer. Now, in English, it's spelled with a K, but there's also a variant where it's spelled with a CH. So the CH is one way of romanizing the letter chi. So this is chi over here. And if you want to romanize this letter, you can spell it with a CH. But because of some abnormalities with English spelling, it is spelt with a K. So this is the same as kilo, like kilogram or kilometer. So that's why we're using chi over here. And chi has the same form as the Latin x. So this corresponds to 1,000 times 5. So we have 5,000. So that takes care of the 6 myriads and the 5,000s. Now we need 500. So we're going to use the pi notation again. So we have this pi, and then we're going to put eta inside. So that's 100. So we used that up here as well. So this gives us 500. And now for 30, that is 3 times 10. So 10, we used delta before. So we're going to write delta, delta, and delta. So we're adding 3 copies of 10. And this delta stands for deca. So we have deca, 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 and that gives us 30. And what about 6? Well, 6 is the same as 5 and 1. So we can write that as pi, and we have 1. So this is used for 1. So we just have a stroke. You can interpret that as a capital iota. So just like this character over here, iota, and you can interpret that as an I. Now let's have a look at the Roman numeral counterpart. So this is 1 is the same. So it's the same symbol in Roman numerals. Over here, we use V to denote 5. So we have 5 over here and 5 over here. So the pi is for penta, and over here we have this V in Roman numerals. And then what about these 3 deltas? We can write them as x's in Roman numerals. So x represents 10. So this might cause some confusion because chi is used for 1,000, like kilo, and over here we're using x for 10. So that is a little bit confusing. Then for this 500, there is a letter, and that is D. D is used in Roman numerals to represent 500. What about these guys over here? Well, we can think of this as 65,000. So we can write this as 65. 65 is the same as 50 plus 10 plus 5. So L is 50, then we have 10, and then we have 5. That gives us 65. And we can write a bar above that, and that indicates multiplication by 1,000 in Roman numerals. So this part is slightly different, because in Roman numerals, we prefer to deal with thousands, but using the Greek system, we prefer to deal with myriads, which are 10,000s. And let's have a look at one more example to illustrate these systems. So let's have a look at 2 to the power of 2 to the power of 4, and we're going to subtract 1 inside of this exponent. So instead of having 16 as the exponent, we're going to have 15 as the exponent. So let's write that in hexadecimal first. So in hexadecimal, we're going to take half of this value. We're halving that value, that's going to give us 8, 0, 0, 0. And an X indicates that this is hexadecimal. So each of these zeros can be thought of as 4 zeros in binary. And this 8 over here, that can be thought of as 1, 0, 0, 0. So 1 followed by 3 zeros. That is 8 in binary. So you can write that out in full in binary notation, or you can write it in a more condensed format in hexadecimal. Next, let's have a look at the decimal representation. That is 32,768. How are we going to write this using the Greek alphabetic numeral system? Well, we have 3 myriads. So we write mu for myriad, and then we put a gamma above. So gamma represents 3. Then we need 2,000. So we're going to use beta, and we need to put a mark over here to specify that it's getting multiplied by 1,000. And then we have 700. So this is 700. We need psi for 700. And then 60. 60 is psi. So we have psi over here. And finally, we need 8. And 8 is represented by eta. So that is eta. And you can also write these using capital letters, but you have to make sure to distinguish this myriad mu from this mu over here. So mu also means 40. So you have 4 times 10. But this mu over here, which looks exactly like the Latin m, that represents the myriad. So that's that myriad notation. And there's other alternative notations where you can write these values to the left, and you keep them all in one line. Now let's have a look at the acrophonic notation. So what are we going to do? We need 3 myriads. That means we need to write m, m, m. So that is 3 myriads over here. And what about this 2 over here? That's 2,000. So we need 2,000s. So that's chi, chi. So you can also refer to this as mu. The Latin m is the counterpart for mu. So you have mu, 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 and then chi, chi. That takes care of 3 myriads and 2,000s. And then we need 700. So that is 500 plus an extra 2 hundreds. We have 5 times 100, and then we have 2 more hundreds. And then what about this 60? Well, 60, that is 5 times 10 plus an extra 10. So over here we have 50 plus 10, which is 60. And then 8 is 5 plus 3. We can write that as 3 bars over here. So these 3 lines, they correspond to 3. And here we have 5 plus 3. And let's also write this using Roman numerals. So the 3 is exactly the same in Roman numerals. And over here, we have a V to represent 5. And we use X to represent 10. And there is a symbol for 50, which is L. And then for 100, we'll use C. We have C, C. And for 500, we'll use D. And what about this 3 myriad 2,000? We can think of that as 32,000. So we can write this as X, 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 and then I. So this is 32, and then we put a bar above, and that allows us to multiply by 1,000. So that is the Roman numeral version. And one interesting feature of Roman numerals is they also have a subtractive property. So instead of writing I, 4 i's, that's the same as 1 less than 5. And if you have 5 plus 4, you can also write that as 1 less than 10. Now, similarly, if you have 40, you can write 40 like this using additive notation, or you can use subtractive notation. You can write it as 10 less than 50. And if you have 90, you can write it as 50 plus 40, or you could also write it as 10 less than 100, which is C. And there's also another example. We can write 400 as C, 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 and alternatively, we can write that as 100 less than 500, which is D. And if we have 500 followed by C, 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 This is 500 plus 400, that's 900, and 900 is 100 less than 1,000. So M is used to represent 1,000 in Roman numerals. But that can be confused with this mu. Mu is used to represent a myriad using the Greek acrophonic numerals. So we have seen the modern positional systems using binary, hexadecimal, and decimal. And we have also introduced this alphabetic Greek numeral system in addition to this acrophonic numeral system. And this old acrophonic numeral system is very similar to the Roman numeral system. It uses additive notation. But keep in mind that the Roman numeral system also has this feature of subtractive notation. So this subtractive notation came later. First, additive notation was used, and then this subtractive notation was also used to kind of summarize these inscriptions, where you would only need 2 characters instead of 4 or 5 characters. So this is a way of condensing the notation. Just like how binary can be condensed using this hexadecimal notation. So you can use this additive notation, or you can use subtractive notation so that you have to use less characters. So these are different numeral systems. And it's important to consider all of these numeral systems as a historical progression, where we work out different ways of representing numbers.